Started and do some physics. Just to continue, just an announcement. I did hand out the first problem set. It will be due on Tuesday at noon. It is 2 and a little bit pages, so make sure that you have both of the pages. One is a double-sided, the other is a little couple sentences on the final page. Yes, and just as a reminder, the TAs have their office hours Friday afternoon at 2 p.m. In room 326, as hopefully I think is on the syllabus. Now, let's go ahead and get started. So last time we were thinking about the theory of special relativity. So I described to you what spacetime was. So spacetime is the set of events, which is to say, which are labeled by 4 coordinates So, for example, in a Cartesian coordinate system, you would label them by 1 time and 3 spatial coordinates. And then the question that we started asking was, what sort of coordinate invariant concepts can we associate with events in space-time? So the actual values of these Cartesian coordinates t and x have no independent meaning in and of themselves, because they will depend on the origin of your reference frame, or the origin of your coordinate system, so there's no coordinate independent meaning to those numbers. But if you have 2 events, say an event at time 1 and position x1, and another one at t2 and x2, then in special relativity, you can define the coordinate invariant notion of the invariant interval between those 2 points. So delta t is the time difference between those 2 points. Delta x is the square root of x1 minus x2 squared, which is the coordinate distance between those 2 points. And because of the relativity of simultaneity and length contraction, delta t and delta x don't make sense in and of themselves in special relativity. But we define the quantity delta s, which was given by the formula minus delta t squared plus delta x squared. Or if we wanted to write it out a little more completely, minus delta t squared plus delta x1 squared plus delta x2 squared plus delta x3 squared, where delta x1 is x sub 1 superscript, you know what I mean. So for example, delta x is equal to x2 minus x1 vector, and then delta x1, x2, and x3 denote the 3 components of that vector. So this delta s is known as the invariant interval between the 2 points t1, x1 and t2, x2. And my claim is that all of special relativity simply boils down to a particular statement involving the invariant interval between 2 points. So, before getting to this formulation of special relativity, let me ask if there are any questions. So typically, we plot points in space-time. So we find it useful to draw a picture of space-time as follows. So typically, we'll draw a vertical time direction, and the spatial directions will be drawn horizontally. Now, of course, space-time is 4-dimensional, and it's difficult for me to draw that on a two-dimensional tablet, so I'm only drawing one of the spatial dimensions here. And then we can look at the behavior of this invariant interval, which is given by delta s squared is minus delta t squared plus delta x squared. So if we set the first point, t1 and x1, to be the origin of this space-time diagram, then the lines of fixed delta s are hyperbolas on this space-time diagram. So, for example, the line where the location of points where delta s is equal to 0 is given by this pair of 45-degree lines on the space-time diagram. The set of points where delta s is positive, or rather, delta s squared is positive, are given by hyperbolas that lie below this 45-degree line. So this is where delta s squared is positive, because delta x is bigger than delta t. And then up here, inside of this set of 45-degree lines, are the hyperbolas where delta s squared is negative, and so that delta s is pure imaginary. So on this diagram, light rays travel on 45-degree lines because, remember, we are using units where the speed of light is equal to 1, so that means that dx over dt, delta x over delta t, will be equal to 1, meaning that a light ray will travel on a 45-degree line, and lines of constant delta s are hyperbolas. Well, they're hyperbolas if I ignore the other two spatial dimensions, and they're hyperboloids, three-dimensional hyperboloids sitting in a four-dimensional space, if I include those other two spatial directions, x2 and x3. So there's a special name that we attach to these three different cases where delta s squared is negative, positive, or 0. So if delta s squared is 0, so that delta s is 0, then we say that the 2 points are quote-unquote null separated. Meaning that these 2 points can be connected by a light ray whereas if delta squared is less than 0, we say that the points are time-like separated. So on this diagram up here, the points where delta s squared is less than 0 are given by this hyperboloid up here. So for example, if delta x is equal to 0, and we're just talking about 2 points which occur at the same coordinate position in some reference frame, then we will say that the points are time-like separated. And in that case, they can be connected by a trajectory which is moving with some velocity which is less than the speed of light. So in particular, if delta x is equal to 0, then delta s squared is minus delta t squared, which is negative. In that case, the trajectory which would connect those 2 points is the trajectory that's not moving with any velocity whatsoever. Whereas if delta x squared is non-zero, but still smaller than delta t squared, you can connect these two events by a trajectory that describes some person or some spaceship or something like that moving at a velocity less than the speed of light. Finally, if delta s squared is bigger than 0, then we say that the points are space-like separated, and they cannot be so connected. In particular, they could only be connected by a trajectory which travels faster than the speed of light, which is impossible. So sometimes we will say that two events which are space-like separated are causally disconnected, and points which are null or time-like separated are causally connected. Are there any questions on that? This is probably a terminology that you've seen before. Have you seen this terminology before? It's certainly a concept that you've seen before. You may not have seen the words null, time-like, and space-like, but certainly the fact that observers, two events which are very, very far apart, with delta x bigger than delta t, cannot be in causal contact with one another. That's probably a concept that you've seen before. Any questions? No questions? All right. Okay, so let's return to the question of special relativity. So the claim that I made at the end of class last time is that special relativity is the statement that for any two time-like separated events, namely two events where delta s squared is less than 0, the proper time, which is to say the time measured by an observer moving at constant velocity between those two events, is given by the formula, it's delta tau, which is given by the formula delta tau squared is minus delta s squared. Remember, for time-like separated events, delta s squared is negative, so delta tau squared is positive in this formula, and delta tau is a real number. If you were to try to compute this for space-like separated events, you would find that it's imaginary. And the claim, which I would like to now describe in more detail, is that this one statement reproduces all of the funny effects that you learned about in your courses on special relativity. Time dilation, length contraction, relativity of simultaneity, twin paradox, whatever that ladder in the barn or something like that. This does it all. Okay. So what I would like to do is just go ahead and unpack this statement for a few minutes and describe for you the manner in which this reproduces all of the funny effects of special relativity. Before I do so, let me pause and see if there are any questions. No questions. Okay. So let's see how this reproduces, for example, the effect of time dilation. So let's consider, for example, the twin paradox. So let's imagine that we have, so let's draw our little space-time diagram here. And let's imagine that we have two twins, one of whom stays on Earth while the other one goes off to Alpha Centauri in his or her spaceship and then returns. And let's see how old those twins are when they when they meet again after the second twin returns from Alpha Centauri. So in this coordinate system, I will take the point x equals 0 just to be Earth, and I will take this to be the inertial coordinate system, which is at rest with respect to the Earth. So that twin 1 will just stay here at some time, for some time interval delta t on Earth, whereas twin 2 will move at some constant velocity to Alpha Centauri before returning at the same velocity in his or her rocket ship to Earth. And what I would like to do is compute the difference in the proper time elapsed as observed by those two twins. So, for example, twin 1, who's at home, the amount of time elapsed is just equal to delta t, because delta x would be equal to 0 for this trajectory at constant velocity connecting those 2 points. Now, let's say that Alpha Centauri is a distance delta x away, so that twin 2 is traveling at a velocity that's given by, let's see, it would be delta x over 2 delta t, right, because this is, sorry, it'd be twice that, wouldn't it? It would be, this is delta t, it would be 2 times delta x over delta t. So that the amount of time that would be elapsed in this interval here, let's call it delta tau 1, so the amount of proper time that would be measured by twin 2 on his or her journey out to Alpha Centauri would be given by delta tau 1 squared, which would be equal to minus delta t over 2 squared plus delta x squared. Or if you wanted to let v be 2 times delta x over delta t, this would just be 1/2 times the square root of 1 minus v squared times delta t. And of course, the same proper time will elapse for this twin on the journey back to Earth. So that will be equal to delta tau 2 squared. So that the total time elapsed, oh, I'm sorry. There's a square everywhere. So let's, there we go. So that the total time that's elapsed for twin 2 relative to twin 1 is given by the factor, the square root of 1 minus v squared, which is the usual relativistic factor that appears when you're comparing time intervals that are elapsed in rest frames that are moving with respect to one another. So this is the usual relativistic time dilation factor. Is that clear to everyone? I went through this a little bit quickly because in your lives as physicists you've probably seen the twin paradox many times. This is just a slightly different formulation of it in terms of the invariant interval, but there's nothing qualitatively new here. Any questions on this? Did I make any mistakes? What's that? Delta tau. Oh, yeah, thank you. Yeah, my batting average is awfully low this early in the morning. So I promise you that I will make mistakes repeatedly throughout this course. Each and every one of them is intentional and is a test of your abilities. So if you don't point them out to me, I'll be disappointed, and my opinion of you will lower considerably. Yes. Any other obvious mistakes here? So, for example, yes. I'm sure I did. Oh, God. Yeah, okay, fine. Thank you. Wait, no. Inside, yes. Good. Excellent. Any other... Yeah, so I generally try and make as many errors as possible in order to give you the most challenging educational experience so that you will grow as physicists. Yes. Any other questions? So through a similar argument like this, for example, we could also, for example, derive length contraction. Shall I go through that? this might be, you've probably already seen the derivation. So once you know time dilation, you can derive every other effect in special relativity, simply because lengths are measured. How do you measure lengths in relativity? Well, you need to have some way of building a clock. How do you build a clock? Well, you need to have, in order to measure lengths, you need a clock, because you measure the amount of time it takes for light rays to bounce off of mirrors describing the length of some object. And so if your clock slows because of the time dilation, hence you have length contraction, hence you have all of the other effects that you're used to in special relativity. So for example, we could go through the derivation of length contraction based on this principle of the invariant interval, but you might find that a little boring, so unless you specifically would like to, I'll just move on to understand the implications of this formulation of special relativity. Shall I do that? Would you like to go through length contraction in a bit more detail? How about this? I will assign to you the following challenge. I encourage you all to, tonight, when you're having trouble falling asleep, try and use this definition of special relativity in terms of the invariant interval to derive the effect of length contraction. And if it doesn't work, then let me know and we'll go through it at the beginning of class next time. That'll be a good challenge. Okay, good. That will save me the embarrassment of making further mistakes in the computation. Okay, so now I'm a lazy person, and I'm especially lazy at 9:12 in the morning. And so, because of that, I'm going to introduce a bit of notation which will allow me to be as lazy as possible. Now, as physicists, it's good to be as lazy as possible, but no lazier. So, what I would like to do is introduce some notation to accommodate my own laziness. So, the invariant interval that we have been considering is the sum of four terms, minus delta t squared plus delta x1 squared plus delta x2 squared plus delta x3 squared. Now, that's an awful lot of terms to keep writing down over and over again. Even the two terms, minus delta t squared plus delta x squared, if I use the three-dimensional vector notation, is still too many terms for my taste. And anyway, in relativity, we're supposed to treat time and space on completely equal footings. So what I will do is introduce a notation where I define the 4-vector x mu, well, it's not really a vector, but the set of 4 quantities x mu to be the packaging of these 4 quantities t and the 3-dimensional vector x into one single symbol. So mu here is an index which will run from 0 up to 3, so it'll take the values 0, 1, 2, or 3. So that, for example, x0 is equal to t, x1 is equal to x1, x2 is equal to x2, which we might call y, if x1 is x, and x3 is equal to x3, which we might call z, if we're using a Cartesian coordinate system. And then, with this notation, delta s squared can be written as the sum over mu and nu of eta mu nu delta x superscript mu delta x superscript nu, where I've introduced the set of 16 quantities here, eta mu nu, which are given by 0 if mu is not equal to nu, and plus or minus 1 if mu is equal to nu. So eta mu nu will be equal to minus 1 if mu and nu are both equal to 0, plus 1 if mu and nu are equal and not equal to 0, and 0 otherwise. So then if you stare at that for a minute, you'll see that this, of course, is exactly the same as minus delta t squared plus delta x squared. And eta mu nu is just the 4x4 matrix with components that are non-zero only along the diagonal and are given by minus 1 in the time direction and 1 in the other three directions. So this quantity, eta mu nu, is a rather special quantity. It is a 4x4 matrix that packages into it the structure of the invariant interval in special relativity, and it has a name. It is known as the metric of flat spacetime in Cartesian coordinates. So that is some progress. Now I no longer have to write down those two quantities, delta t and delta x, separately. But I am in an especially lazy mood this morning, and so I will introduce another piece of notation. So I will leave off the summation symbol and just write delta s squared is eta mu nu, delta x mu, using what is known as Einstein Summation, the Einstein Summation convention. So in the Einstein Summation convention, repeated indices are summed over and in particular, we will only allow our expressions to have one upper and one lower index summed over. So an index can be repeated only if it appears once as a subscript and once as a superscript. So, for example, the expression, A mu, B mu is the sum of over all values of mu of A sub mu, B sub mu, but an expression of the form A mu, B mu is nonsense and is not an expression that we know how to make sense of in the Einstein Summation convention. So at this point, the demand that we only have one index as a subscript and one as a superscript is simply an irrational demand that I am making on you. But within a week or so, it should become extremely obvious why this is a supremely intelligent thing to do. Yes, question?
Why can't you understand that second expression as a new vector with every coordinate sum?
That is you could try, because it will turn out that such a thing is not a vector, in the sense that I have not defined vector yet. So the reason why the summation convention is so picky is that it will allow us to manipulate expressions in a coordinate invariant way. As I articulated last time, our guiding principle will be the principle that the laws of physics should be independent of what coordinate system they are written in. So, for example, if A mu is the set of components of a vector written in a particular coordinate system, and B mu is the set of other components of a vector written in the same coordinate system, then the set of four quantities A0, B0, A1, B1, and so on and so forth is not a vector in the same sense. So we will go through this in some detail. But for now, you'll just have to trust me that there's a deep rationality in this choice of conventions. Presumably, you have all seen the Einstein Summation convention. If you have not seen the Einstein Summation convention, don't lose heart. You are going to see a lot of it. it's one of those things that has absolutely no physical content whatsoever, but once you get used to it, there's no going back. And it makes our lives considerably easier. People do always get tripped up on the business of upper indices versus lower indices. People always make mistakes at the beginning in this regard, so it's just something you'll get used to. So, are there any other questions? So let me introduce another little definition here. So, in special relativity, intervals are measured using the metric eta mu nu, so that delta S squared is eta mu nu, delta X mu, delta X nu. So that sentence, yes? Question?
What's the difference between upper indices and lower indices?
We will learn that. So right now, I have not told you what the difference between upper and lower indices are. I've only told you that upper indices describe displacements between coordinates in, say, a Cartesian coordinate system. I have not told you what the physical meaning of a subscript coordinate is, but I'm reserving it for future use, if you know what I mean. And we will learn. We will work through, by working through the definitions and working through the implications of coordinate general covariance, we'll understand exactly what it is a lower subscript on an index means. So I'm being very careful here. I'm introducing notation before we need it, just so that you get used to seeing upper and lower indices treated very carefully in this respect. Often, for example, when you're doing vector calculus or electromagnetism, you're not very careful with upper and lower indices because it doesn't matter in those contexts. In the context of special and general relativity, it's very important for reasons that we'll describe it very explicitly this and next week. Yes?
How can you tell if it's an upper indices or upper index or power?
Context. Generally speaking, if there's any ambiguity, I'll try and not be ambiguous. But you know, there are only a finite number of symbols in that I have at my disposal. I'll try and strive for lack of ambiguity, but I won't always succeed. So, for example, delta S squared, through context, you can understand that this is the square of a quantity rather than the second component of some vector, for example. Good question. Other questions? Okay. So, this sentence that I have written here, that in special relativity, intervals are measured using this particular metric, which in the Cartesian coordinate system is a diagonal metric with plus and minus 1 entries. That's a rather long sentence. And in fact, there is a shorthand for this sentence, which you may have encountered before. So this statement is sometimes referred to as the statement that in special relativity, space-time is given by Minkowski space. Minkowski space is just a name for space-time in special relativity. It's useful to learn that name because soon we will learn about other spacetimes, which are not Minkowski space. And there's a symbol that we use to refer to Minkowski space. We call it R with the superscript 3, 1. That's just the symbol that we use to refer to Minkowski space. So R has something to do with the fact that the coordinates of Minkowski space are real numbers. The 3 refers to the fact that there are 3 spatial directions, and the 1 to the fact that there is 1 time direction. So, you are also familiar with other sorts of spaces. So, for example, at some point when you were in middle school or high school, you met the space R2, which is Euclidean two-dimensional space. So that's just the plane. Why is it called R2? Well, it's called R2 because the distance between 2 points is given by the Pythagorean theorem, which you can see takes a form which is very similar to our expression for the line element in special relativity. Likewise, R3 is the Euclidean three-dimensional space that you learned all about in your vector calculus classes, for example. And this is the space that you typically spend a lot of time thinking about when you study electromagnetism. So R3 is the three-dimensional space where distances are given by the three-dimensional version of Pythagoras' theorem. And you can see that the symbol R3, 1 makes sense because we now, in special relativity and Minkowski space, have 4 coordinates, but there's a relative minus sign between the spatial and the time coordinates, which is why we use that funny symbol R3, 1. And sometimes we say, we use the following semantics. We say that R31 is a Lorentzian space because one of the directions is time-like in the sense that there's a minus sign in the expression for the invariant interval, as opposed to R2 and R3, which are Euclidean, in the sense that there are only plus signs in the expression for distances in the Pythagorean theorem, and that the standard rules of Euclidean geometry apply. So I haven't really done anything for the last 30 minutes or so. I've just introduced some notations and some semantics. I am trying to be as precise and as careful as possible here, because, as you may guess, all of the words that I am introducing will become very relevant and very important in the next few lectures. So I would now like to actually do a little bit of physics. Before I continue to do that, however, are there any questions? Okay. Yes? Sorry, right here? That's supposed to be a delta z squared.
What's the R2?
Yes?
R3.
Yes?
What's it for R3, 1?
R31 is Minkowski space, and so the distance between 2 points is the quantity that we usually call the invariant interval. So that's what I've been calling delta s squared, and it's given by minus delta t squared plus delta x1 squared plus delta x2 squared plus delta x3 squared. So this formula for delta s squared is, of course, reminiscent of the Pythagorean formula for distance, but with some funny-looking minus sign. And in fact, it just tells you that there's a geometry associated with Minkowski space, with spacetime and special relativity, which is very similar to, but somewhat different from, the usual geometry associated with Euclidean space, as you learned in high school when you took your geometry class. Other questions? Okay. So, life would be rather boring if we only traveled at constant velocity all of the time. So, what I would now like to begin to do is consider the possibility that we want to study the physics of observers who are not moving at constant velocity, and who are moving on some more complicated path through space-time. So, a path through Minkowski space, i.e. a path through R3, 1, which is space-time in special relativity, is known as a world line, and is parameterized by 4 functions. So if a point in Minkowski space is given by the quantities x mu in our Cartesian coordinate system, then in order to describe a path through that space-time, I need to introduce some continuous parameter lambda and tell you how it is that those 4 quantities depend on lambda. So I'll need to tell you t of lambda, x1 of lambda, x2 of lambda, and x3 of lambda, where lambda is a continuous parameter which labels points on this path, or this world line, through space-time. This is a physics class, not a math class. So when I say words like continuous and smooth, they mean exactly what you think they mean. If in your mind you have some very complicated definition that you might have learned in some math class, that's fine. You are welcome to that definition if you please. If you have no such definition in your mind, that's fine. Also, it just means what you think it means. So if I wanted to be terribly precise, I would say it's a parameter which smoothly labels points on this path, in the sense that the various quantities t of lambda, x1 and lambda, and so forth, can be differentiated an arbitrary number of times with respect to lambda. But of course, we're physicists, and so that doesn't particularly matter to us. So the question then, yes?
If we are in R3 and we have some built-in, consider the parameter for the flat as being time in
Yes.
this space, is there like a way of thinking about lambda that is similar?
Yes.
What is it?
Lambda is the parameter that labels different points along the world line. If I, for example, am moving in a path through space-time on some rocket ship that's accelerating in some funny manner, there are many different parameters that I could use to label my path through space-time. I could use one very natural choice would be my proper time as measured by a clock that I carry with me. But that's not the only time that I could use. For example, if you're sitting in Houston tracking my progress, it might be more convenient for you to use a clock which is at rest with respect to you, on Earth, which would be a different parameter that would be used to label this world line. And in general, of course, there's no right or wrong answer as to which one is the correct parameter to use to label my path through space-time. Some of them are useful in some contexts, some of them are useful in other contexts. So, yes, but lambda, for example, could be the time as elapsed by some observer that is moving in some way. There may be more or less convenient choices for the parameter lambda, as we will see in much greater detail when we consider the geometry of world lines later in this course. So the question that we would like to ask now is, what is the proper time measured by an observer who is moving on this world line? So let's say, for example, that we have say an observer who begins here and ends over here, traveling on some complicated path through space-time, which is not a constant velocity, but is just given by these functions x mu of lambda, and moving between some initial point x1 and t1, given by some initial value of lambda 1, and some final values x2 and t2, at which lambda is equal to lambda 2. And we would like to ask, what is the total proper time as measured by an observer moving along this world line? Now, of course, that proper time is given by the square root of minus delta s squared, where delta s squared is the interval along that world line. And that interval is computed by doing an integral along that world line. And what we would like to do is understand what that integral formula is for the total invariant interval that is measured along this curved world line through spacetime. So how do we compute this interval? Well, what we imagine doing is we imagine chopping up this world line into a lot of little different bits. So we imagine that we're looking at a particular point along this world line, and although the observer is not moving at constant velocity, if we restrict our attention to a very small neighborhood of this point, then you can treat this observer as moving at constant velocity. And so you can examine you could imagine you have a very small change in the coordinate x dx and a small change in the time coordinate dt, and then you could compute the interval ds corresponding to that small change in x and t. So delta s then will be given by an integral, and it will have to be an integral over lambda, since everything depends on lambda. And it will just be the integral of the invariant length over lambda, where we treat the particle as moving, the observer as moving at constant velocity at any given instant, and then integrate that expression for the invariant interval over lambda. So it'll be given by the integral of the square root of minus dt over d lambda squared plus dx1 over d lambda squared plus dx2 over d lambda squared plus dx3 over d lambda squared. And this is integrated d lambda from lambda 1 up to lambda 2. Now, hopefully this expression is not too surprising to you, because if there wasn't that funny minus dt by d lambda squared term, this would be nothing more or nothing less than the expression for the length of some curve through three-dimensional space as you would have learned in your class in multivariable calculus. So all we have done here is now account for the fact that the metric of Minkowski space, eta mu nu, has that funny minus sign, which will lead to this negative term in our expression for the square root. Now you might worry, of course, that the quantity in the square root could be negative, and so that what you would get is imaginary. But in special relativity, any observer can only travel at or less than the speed of light, and which means that the quantity in the square root always has to be positive, so we'll never run into that problem. So if I wanted to write this a little more succinctly, I would just write this as the integral d lambda of the square root of eta mu nu dx mu d lambda dx nu d lambda, where dx mu by d lambda is just the set of 4 derivatives of the coordinates x mu with respect to lambda. Or I could write this as even more succinctly as the integral d lambda of ds by d lambda, or just the integral of ds along the world line, where I have defined the quantity ds by the expression eta mu nu dx mu dx nu. So the symbol ds here is just the infinitesimal version of delta s. So the formula that I wrote for delta s squared was the formula for observers moving at constant velocity. And I am using here in my formula for the invariant interval measured on a world line an infinitesimal version of that formula, which I call ds rather than delta s, to remind myself that this is an infinitesimal expression for the invariant interval. So in this formula, dx mu refers to some sort of infinitesimal displacement of the coordinate x mu, and ds refers to the resulting change in the invariant interval. So, for example, light rays travel along trajectories where ds is equal to 0, and massive objects will travel on trajectories which are time-like in the sense that ds squared is negative, which is the statement that the velocity, the instantaneous velocity at any given time, is less than that of light. And the quantity ds by d lambda, which is equal to the square root of eta mu nu dx mu by d lambda dx nu by d lambda, has a very simple physical interpretation. It's simply that d tau by d lambda, where tau is the proper time as measured by an observer moving on this world line, is given by minus ds by d lambda, so that d tau by d lambda is the rate at which an observer's clock ticks. If this observer is moving along the world line x mu of lambda. And when I say the rate at which the observer's clock ticks, I mean the number of ticks as measured with respect to the coordinate lambda. So, for example, if lambda, as we discussed earlier, is given by my proper time as measured along this world line, then of course d tau by d lambda is equal to 1. On the other hand, if I'm moving on some spaceship that's accelerating around the universe, and you're sitting at home on Earth, and lambda is your proper time and not my proper time, then d tau by d lambda and ds by d lambda would not be equal to 1. It might be less than 1. Yes?
Instead of 1, it shouldn't be an I, because d tau is I times dx.
Oh, I'm sorry, you're right. Yeah, you're right. Okay. Does that make you happy? Thank you. Yes. So, as we have seen, then, special relativity is the statement that in Cartesian coordinates, the line element which is the name that we give to this quantity ds that we integrate in order to obtain the invariant interval, is given by the formula ds squared is eta mu nu dx nu, where eta mu nu is a constant matrix with non-zero entries only in the diagonals. And the basic idea of general relativity is the following. In general relativity, the basic idea is that invariant intervals are measured using a line element that, again, one integrates to obtain an invariant interval. But this line element is no longer given by a constant matrix for the metric, but is rather given by some complicated functions g mu nu, which will depend on the coordinates x mu. So, I'll just write it as g mu nu dx nu, where g mu nu is, in principle, a complicated function of x mu and x nu. And g mu nu has a name, and it is known as the metric of spacetime. So, in order to understand that, I will need to provide some motivation for the statement that gravity is equivalent to allowing the metric of spacetime to be non-constant. And in order to motivate that, we will need to understand something which is known as the equivalence principle. And that is a deep and beautiful subject, which is probably the central physical observation that is at the heart of general relativity. And that's a subject which we will study next class. So this concludes what I was planning to say about special relativity. Next class, we will discuss the equivalence principle. That will probably take no more than half a class. And then from there, we will begin our study of differential geometry. Again, it will be a rather gentle study of differential geometry relative to what one might find in a class called differential geometry. And it will be one which will be motivated by our considerations of coordinate transformations, world lines, and the various other concepts that we have encountered today. So maybe before you guys all leave, there are two orders of business that we should discuss. The first is our TA is sitting in the back. So one of the TAs you met last time. The other TA is sitting right here. So say hello. Simon Archambault, did I pronounce that correctly? Okay, more or less correctly. Good enough. Good enough. So this is your TA. The other thing that we should discuss is the time of the course. Maybe I'll stop the recording so that